What's going on, guys? Welcome back to Dennis Simplifies. In today's video, we'll be going through the Romberg method in numerical methods, right? So sit back, relax, and as you already know, let's simplify. So as you are used to it already, we always try to solve problems to understand the method, okay? So here we are going to solve the integral of 1 or 1 on 1 plus x dx using Romberg method with two sub-interval. Compute your initial values using the composite trapezium method. Perform two iterations, okay? So with the Romberg method, what we do is that we actually use a composite trapezium method and then we refine the values. So we refine the values so that we can get close to the actual answer. So let's say if I ask you, what is the area of a rectangle? You straightforward tell me that it is the length times the breadth, right? But if I ask you, what is the area under this curve? Then you start to fumble, right? So what we are trying to achieve here is that under this curve, it's not going to be easy for you to tell me what the area under it is. So we're going to do is we're going to use a particular method, which is the composite trapezium method, to find the approximate values. We can approximate, we can estimate some values of the actual area. And then when we get those areas, we can refine them so that it can actually it can get close to the actual area under the curve. So what we're doing is that we're using the composite trapezium method to find those approximations. And once we get them, we use the Romberg extrapolation or the Richardson extrapolation method to refine those values to get closer to the area under the curve. Alright, so over here we've been given that we are starting from 1 to 0. Okay, over here we have from 1 to 0. Where's my laser? 1 to 0. And then again, so we are taking the 0 to be the A value, then the B to be 1. So we are from 0 to 1. Then we are given two sub intervals. Okay, so that's n equals 2. I'll explain this as we go along. So this is the formula for the composite trapezium or the formula for the composite trapezium method. So don't let it scare you, we'll get through it. So this is what I'm talking about, where h equals b minus a on n. So this h, as we have, you say the interval is from 0 to 1. Then this h is the step length. That is, if I add h to 0, I keep adding h. By some time, I'm going to get to this one. So the step length is the h. So the h is the small values I will keep adding until I get to the final value. So if I divide it into small sections, that is going to be this h. Okay. So how do we get this h? We get this h by subtracting the 0 from the 1 divided by the number of sub-intervals. Okay. All right. So now let's move on. So we are given 1 on x. So once you have the value for your h, right? Once you have the value for the h, you're going to draw a table, and then the inputs of that table, you use this formula to compute the area. So let's start with that. So we have 1 on 1 plus x. Okay. So we are going to go ahead and find our h. And then when we find our h, we can get some values to put inside this formula. So see from here. So from this table, I said my h was 0.5 or 1 on 2, which is 1 minus 0 divided by 2, right? That's how I got my h. 1 minus 0, so 1 minus 0 divided by 2, I'm going to get 0.5, which is 1 on 2, okay? So now with this h, I'm going to create a table. And the table, I have x and f of x. So you can see we have some variables inside this formula here. So I'm starting from 0. Remember, from here, we are starting from 0 to 1. So I start from 0, and then I add 0.5. So 0 plus 0.5, I have 0.5 for x1. Then I add another 0.5 to get to 1. Now when I have this value, this x values here, I'll come here, then put the value of this x0 in here. Then I'll get my f of x value. Then I come and put the value of x1 here to get my f of x1 value here. Then come and put this one also inside this formula here to get my f of x2 answer here. Okay. Then from here, I can pick the values from this table and insert them into this formula to find for my first initial approximation. Okay, so we are finding for some initial values first before we refine it to get the to get an approximate or an estimate of the actual or the exact area under the curve. So we go ahead. I'm going to put it inside the formula. So we said h on 2 from here, h on 2, which is 0.5 on 2. Then f of x naught. F of x naught is 1 plus 2 times everything inside the bracket here. So 0.667 is the same as 2 on 3 plus the last value, which is 0.5. Okay, so when we do it, this is going to be our first initial approximation. So for our first initial approximation, we are going to have 0.70833. So that's our first initial approximation. That it could be, is we are approximating, we want to find the area under the curve. We are approximating, this could be the area, but this is not the exact area of the under the curve. We have to keep improving it. So we said here that where h I times h, so the initial values. Now to find the next initial value, we are going to take this h value and divide it by 2 again. So if you make it very small, we can find the area. Okay, we can keep improving the answers that we are getting. We want to keep improving it. So when we decrease the area, we decrease the size of this step length, the h, we can get another area which will be better than the one we had before. Alright, so we want to decrease the h value, the step length, and then find the other area to get another initial value, so that we keep improving it to find the actual area. So let's move to the next one. For the second initial approximation, as I said, we're dividing the h by 2. Alright, so this is the h, what I drew before. Then to divide it by 2, initially we have the h to be 0.5, which was 1 on 2. So if we divide it by 2, we get 0.25. So with this h value, we can draw a table, right? When we draw the table, this time we are starting from 0, then we add 0.25 to it, another 0.25, another 0.25 until we get to 1, which is the final value here. Then we come and put the x value, which is 0, inside the formula here. Alright, then we get for our f of x value here. Then we put the x1 again to where the x is. To get our f of x1, put the x2 here. To get our f of x2, put the x3 inside here. To get our f of x3, then put this x4 value, which is 1, inside this formula here to get our f of x4. Alright, then when we have these values here, we can use the composite trapezium method to find our second initial approximation. I'm going to put it inside the formula. We have our h to be 0.25 divided by 2, then into brackets 1 plus 2, then the values here 1, 2, 3, all in brackets. We multiply all of them by 2 plus the last value, which is 0.5. Then I'll get my second initial approximation. So you can see that this approximation, this area here, is better than the one that we had before. The other one we had 0.7. So you can see this one has come a little closer to the actual answer that we are looking for. So we are keep improving it. So again, we are going to keep improving it to find for our third initial approximation. And that one, we are going to divide this h value again by 2. Alright, so that it becomes very small, and then we find for the area again. So the more we keep decreasing, the more we keep improving our value. So let's move to that side. For our third initial approximation again, we are going to divide the h by 2. As I said, we are going to get 0.125. Then with this h value, we can draw our table. When we draw it, we're going to get h is equal to 1 on 8. Okay, then we are going to start from 0, as you know from here. We start from 0, then we add the 0.125, we add the 0.125, we add until we get to 1. And when we get to 1, we are going to use this formula over here and put a 0 inside the formula. We are going to get f of x naught to be 1. Then put the 0.125 also here. We are going to get f of x1 to be 819. Then put the 0.25 also in there. We are going to get 0.8. So you keep putting the x values inside until you get to the last one, which will be 0.5. Okay. So now again, you use the composite trapezium method formula to find for your third initial approximation. You start with h on 2, which is 0.125 on 2. Then you start from 1 plus 2 times the values here. Right, you multiply these values here by 2 plus the last value. Then you're going to get your third initial approximation. Alright, so this is our third initial approximation. So when h was 1 on 8. Alright, so now that we have for our first, second, and third initial approximation, you can actually notice that as we did our approximations, the values kept improving. You see, the values kept improving. The area under the curve kept improving. But again, this is still not the actual one. Now we want to use the Richardson extrapolation method to refine them, make them better than they are now. Right now, if we can keep on doing this, and they will still not be better. But with the Richardson extrapolation method, it can make it far faster and better. So we're going to use that method to refine the values here. And so let's go there. So we have found for our three initial approximations. So using the Romberg extrapolation procedure, which is the formula that we have here, we can use this formula to refine the three approximations that we have found, right, to get the actual area under the curve. So let's see. So we are saying that when so we have each each over here. So when m is 1 and h is 1 on 2, right? So we can use this formula to find for our first one, our first repetition. So over here, we said we are doing only two iterations, okay? So we'll be doing for m1 and then m2. You can see m starts from 1, 2, 3. We're doing only two approximations. So only two iterations, so just 1 and 2. So over here, we are starting from 1 and then half. So if you put the values inside here, we are going to get 4 and then 4 I naught 1 on 4 minus I naught times 1 on 2. Okay, so this one here is our second initial approximation. If you remember, we had I naught times 1 on 4 when h was 1 on 4. If you remember that here this h here is 1 on 2. So 1 on 2 divided by 2 gives us 1 on 4, right? So when I naught and then 1 on 4, that's this value here is our second initial approximation, the value that we have for our second initial approximation. So we're going to put that over here. Then this I naught and then 1 on 2. This one was our first initial approximation when h was half. Okay, so you put that one also over here, and then you do the down part here and you get 3. Then you're going to find for your first value. So this is for your first iteration. So we can do for our next one when m is 1 and then h is 1 on 4. So again, you put when m is 1 inside here. Then we said h is 1 on 4. So that was going to be 1 on 4 divided by 2. We get 1 on 8. Okay. Then over here too we have this. So you know that this value here, 1 on is 1 I naught and then 1 on 8 here was our third initial approximation. Our third initial approximation. So we put that value over here. Then this I naught 1 on 4 here was our second initial approximation. So you put that value also over here, all divided by 3. And then we get this value. Alright, so you can see that we are on it, and then we are doing just two iterations. So we end at when m is 2. So again, we put them inside when m is 2 here, and then when we do it, you can see over here when I1 and then 1 on 4 and then I1 when 1 on 2. Okay, we know the value for when I1 and then 1 on 4. For I1 and 1 on 4, you can see we had it over here, I1 and then 1 on 4. We had this value. So you can pick this value here and put it over here. So times the 16 minus I1 and then 1 on 2. I1 and 1 on 2, we have the value here. I1 and 1 on 2, which is this. Okay, so we put that value to also here. Divided by the 15, we are going to get this value. So we have seen that we have refined the approximations that we did from the composite trapezium method. We have refined it and made it better using the Richardson extrapolation method. We have actually made it better this way. So we can keep on doing the iterations until okay. But we are going to end here. The question says we should do only two iterations, so only up to when m is equal to 2. Alright. So if you do this on your calculator, you're going to see that the exact solution is 0.693147. And then when we did our iterations, we had 0.693148. So you can see that the magnitude of the error was very, very small, 0.00001. Alright. So friends, that's basically it. So you first use the composite trapezium method to get your initial values. Then from there, you use the Richardson extrapolation method or its formula to refine those values to get the actual or get closer to the exact solution that will be the area under the curve. Alright, so friends, that's basically it. Don't forget to like and subscribe. Ask your questions in the comment section or give any comments in the comment section, just to motivate us. And then share with your friends and then make sure you subscribe. Until next time, apatia.